verify when you see the presentation.
Yes, I see
Perfect.
it.
So thank you very much for joining us here today on the big topic of fouling in heat exchangers. My name is Adam Dahlqvist. I've been working with SWEP since late last millennia, and I'm Swedish, but I live here in the US. I will guide you through this presentation. I will start with a disclaimer that I actually added this morning. Everything we will present today is written in with the best, in good faith, the best information we have with the best intentions. However, we do not take any responsibility for our advice in the way that we really want to help you to reach the best results. But since we are a component manufacturer, there are so many other moving things out there, water quality and etc. We will like to help you, but we cannot take any warranty on our words. But let's get to it. See if perfect. So we start this. What is SWEP? SWEP is a US-owned, Swedish-based brazed plate heat exchanger specialist company. The headquarters of SWEP is in Landskrona, Sweden, where we have one of our factories. The other one are in Slovakia, Suzhou, China, Kuala Lumpur, Malaysia, and for the US market, North American market, we have Tulsa, Oklahoma. We are since 1994 part of the Dover Corporation, a US industry group that is much bigger than we are. SWEP is about 1,000 employees, and we are serving about 16,000 customers worldwide. Those customers are using about 3.5 million heat exchangers every year, and we supply them through our 5 factories that I just showed you. SWEP is we have ISO 9001, 14001. We take quality very seriously. Our heat exchangers are AHRI certified, and we are also member of the following organizations. We are for example, IDEA and ASHRAE, to notably, and then also other ones in Europe and elsewhere. These are some of our customers that we are supplying to. You might find your company there or not, and we will be happy to put your company name up here if you would like to. 2 words about the brazed plate technology. There are other webinars who goes more in depth about this. This webinar is about fouling, so I will be very brief here. The brazed plate heat exchanger is made of channel plates, which are the one creating the heat transfer area. We have a start plate and an end plate to, so to say, put everything together and make them strong to keep the pressure. All the main components are made of stainless steel. The end plate, the channel plates, the connections, everything is stainless steel. And in between the plates, there is a metallic filler, which normally is copper. And during the manufacturing process, where we put these heat exchangers in a furnace, the filler material becomes like a metallic glue, keeping the stainless steel plates together. So once they are baked, they are hermetically sealed of very good strength and heat exchanger efficiency. So once they are produced, you will see that like any plate heat exchanger, we have alternating hot and cold channels. So 2 plates make 1 channel. So every 2 new plates make another channel, where there will be alternating of the warm and cold, etc. of the media. So it becomes very a large surface area with very efficient heat transfer. And since there is no plate and frame around it, it's a self-containing structure. So there will be about 95% of the material will actually be used for heat transfer. And here is also an image showing that, with the different plates you have cold, hot, cold, hot. Just to give you an idea, right? We'll come back to this later. This will be important later on. Something else I would like to say 2 words about is that the plate heat exchanger is a relatively old technology. We're talking about 1800s when it became more popularly used. But what SWEP has been able to do, since it's a brazed plate heat exchanger and it's self-contained, is to work with CFD, computational fluid dynamics, or as we also called it, BPHE genetics. So we are improving it before it's born. So before we make a new product, we do a lot of simulations, making sure that any low flow areas or areas where there is dead areas or low flow that will reduce heat transfer efficiency, but also create areas where fouling is more likely to initiate and propagate. We develop around it so that we have a better developed flow geometry than traditional plate and frame heat exchangers that are, that have to rely on that does not have the self-supporting metallic glue, as I mentioned before. So they don't have as many degrees of freedom for designing the plate as we do. 2 seconds about this one, since this is not a product presentation, but the smallest heat exchanger we have is the B3. It's an iPhone 4S size, and the biggest one we have is a 6-inch port, 4 feet something heat exchanger that will take several megawatts of energy transfer and everything in between. And we also have double wall heat exchangers for tap water production. But please reach out to us for more information about this. So where are we now? Compare the BPHE to plate and frame and tubular heat exchangers. I will just take a small pause and change, because it's changing my timings. So I am back now. I apologize for that, and we're back. So let's compare the brazed plate to other heat exchanger technologies. What I'm trying to show here is, I am biased without a doubt, but I'm trying to show what is the pros and cons of the brazed plate, the plate and frame, coaxial heat exchanger, and shell and tube heat exchanger. When the footprint, the BPHE is absolutely the winner compared to the coaxial and shell and tube that requires much more space. The brazed plate also wins over the plate and frame, since the plate and frame needs to have a service area to be able to utilize that. You can open it, and when they have to change gaskets. Weight, again, the brazed plate is a clear winner with a action at minimum 2 and upwards of weight per BTU. The possibility to add capacity. Both the shell and tube and coaxial are made to that capacity. You could add some extra tubes in a shell and tube, but it's still made based on how many tubes you can fit in it, right? With a plate and frame, you can open a plate and frame and put inside extra plates. And with a BPHE, you can have a booster package with a standard capacity, and then a booster package to add capacity. Gasket-free. Gaskets are not a good thing because they degenerate over time. So we have the coaxial and brazed plate that do not have gaskets. Shell and tube has, a little bit, but they're kind of they're not so they're not covering the whole product. And plate and frame are absolutely dependent on it. So I would say the most sensible to gasket failure is the plate and frame. Efficiency as a heat exchanger, plate and frame and brazed plate are in the same area. We have the coaxial and shell and tube that are worse, and this is considering for the same surface, active surface area. Price efficiency is a very common question, I would say. And if we are looking at the same NTU rating, same heat exchanger efficiency, the plate and frame and brazed plate are clear winners compared to shell and tube and coaxial. And then the last one, which we'll see will be a big discussion point here today. open for mechanical cleaning. So we have shell and tube and plate and frame that you can open and clean inside. And then we have coaxial and BPG that is not possible to open and clean inside. And if we take a step back and look on this table as a whole, the brazed plate is, so to say, the winner, except for this one here. And this is the main counter argument to brazed plate heat exchangers. So I'll try to make you see what I see when it comes to brazed plate and cleaning, and why this point here is not a big issue and might even be an advantage. So where will we start today? So there is a lot of things to say about fouling, and I had to make it simplified. So fouling is macro fouling, suspended solids or fibers that are too big to pass something. Micro fouling, dirt and other things that precipitate, particulate buildup, sorry. Chemical fouling, scaling, corrosion, when corrosion is forming inside the heat exchanger or something else, typically rust. We will not talk about this a lot today since the brazed plate is made of stainless steel, there is no rust buildup. So corrosion is we're going to speak the least about. And biological is, again, it's mostly when it's surface water or seawater, and I will put that into macro and micro to simplify things. And for those of you who ever been to IKEA, I will help you find the exit fast. I will now, this is the last slide of the presentation. So if you check out early, this is what I want you to bring with you home. And I'll go through this fast, and I will go in depth of this slide as we move on through this presentation. To have less problem with fouling, make sure that the selection is with turbulent flow and with a sufficient shear stress. Note the starting point of pressure drop when you commission the system. Use a strainer about 16 to 25 mesh. The smaller the heat exchanger, so to say, the higher the mesh number in some way. That one will stop for the blocking. Make sure that you know your flow. If you have a flow, make sure that you verify it. Have a flow sensor or a smart pump to make sure that you have the flow that you think you have. Keep eye on the system. If the pressure drop over the system increase more than 30% from your reference point, you probably need to do something about it. Cleaning your place could be necessary. And then water is an incredibly complex matter, and the chemistry of water is immense. If you have a system where microfouling, where there is a lot of silt accumulating, you should probably put some kind of bleed off filter or cyclone filter to make sure that the concentration of small particles doesn't increase. And use all the recommended water treatments that are out there. SWEP is not a water treatment company. There's a lot of them out there. So if you're working with tough water, get some help. That was it. So let's go into depth. So now we are tips to avoid common types of fouling, the in-depth method. So what will we focus on today? Well, I already mentioned macro fouling or blockage, when particles and fibers get blocked into the port. Think of it as a stone getting swooped up by a sieve, and make sure that you have a sieve so you don't have to use the heat exchanger as the sieve. Micro or particulate fouling, whatever comes in the heat exchanger must go out. Turbulence and shear stress is key to make that happen. And then we will go in the end versus chemical fouling or scaling, which is very much related to water quality and pH, but also avoiding a high wall temperature. And then that is where the heat exchanger comes in. And as I will say 2 words about Celix as a solution to scale. So let's start with the first one, macro fouling. And as you see this slide here, there's a lot of text. It's hard to write. It's hard to give information about fouling without writing a lot of information. I write a lot of text for you to be able to read this when you receive this presentation later this week. But I will focus on the bold material here. So, what is macrofouling? Anything larger than the channel size that gets stuck in the port of the heat exchanger. If it gets stuck there, blockage, this stuff, right? They will start to trap more material and greatly increase the pressure drop over the heat exchanger. By doing that, it will also reduce the flow if the pump is the same, right? And that will cause secondary microfouling inside the plate. Where do we see this most often? Well, kind of common is if a system is not cleaned out before commissioning. You will have a lot of scrap inside the system and the closed loop when you start. That is supposed to be cleaned out during commissioning using filters and strainers and stuff. Sometimes yes, sometimes no. So that's a one-off problem, a poorly commissioned system. That is, fairly common. Once the system is up and running, closed loop systems is not a problem for this one. The bigger problem is with open loop systems with cooling towers or surface water, where there is a continuous risk of big material being sucked into the system. How to avoid macrofouling or blockage? There is, as I mentioned, blockage is when the particle is too big for the channel size or the hydraulic diameter. A hydraulic diameter of a SWEP brazed plate heat exchanger is between 2 mm and 5 mm, or about a 1/12 of an inch to a 1/5 of an inch. That is the total distance from over this one here. That is too big. So we recommend a strainer of about 16 to 25 mesh. 16 would be for the larger one and 25 mesh would be for the smaller press depth. In that way, the particles end up in the strainer before the heat exchanger, so you don't get stuff inside the heat exchanger. And I would say by using a strainer, you're not only protecting the heat exchanger, but also the pumps, the valves, and other components against wear, erosion, or any kind of malfunction due to external particles. I would also like to issue a warning of using a too high mesh rating. More is not always better. So if you start to use a mesh that is even higher than the 25, 30, 40, that means that they will stop smaller and smaller particles. What will happen then is the strainer will fill up faster, and there is an increasing risk that with the more fine strainer will cause frustration for the caretaker. So that person will, instead of cleaning it once a month or once every quarter, he has to do it so often that he says, screw it, I'll take it away. It shouldn't happen, it does happen. So use a strainer, yes, don't use too much. That was it. Microfouling. Here will be a little bit more, stay a little bit longer. So what is microfouling? It's suspended small solids that settle inside the heat transfer surface. Where do we see it the mostly? Well, where there is continuous accumulation of small particles. What do I mean by that? Well, where there is an addition of dirt over the lifetime of the system. Again, open loop systems return here as a risk factor. Also, open loop groundwater loops, when you dig it down in the ground and get up, if you start to leak in clay and other things. Another one is closed loop with infiltration, if they're old and broken and you start to have infiltration of bad water, or even corrosion of gray steel pipes that will start to corrode. You can have this accumulation of small particles. How to avoid it? We will look more into detail next slide on turbulence and shear stress, but that is very, very important. What comes in must go out. Right sizing the heat exchanger will also be a separate slide. Something I will mention just here is, proper installation. As a heat exchanger that is standing up like this will have less precipitation of fluids than a lying down, because in a lying down heat exchanger there is more horizontal surface that will accumulate for the that will allow the particles to accumulate. And think of it as a desk. A desk will accumulate a lot of dust because it's there, right? It's a big horizontal surface, and if you put it up against the wall, there will be less dust on the desk, because there is no gravity pulling the dust to the desk. Okay, that was maybe not the best allegory. If system is accumulating particles, if you're any one of these the closed loop with infiltration or an open loop, consider to use a filter, a cyclone filter or a bleed off filter, so that you can control the total concentration of suspended particles. The more you have of the suspended particles, the more you will have a risk of it accumulating in key parts of the system, heat exchangers, pumps, everywhere. Okay. Now we are looking into the turbulence and shear stress. I said that this was important, and it surely is. So, turbulence, what do we mean here? Well, turbulence is measured by the Reynolds number, and there is the critical Reynolds number is when we go from laminar flow, where the flow is, so to say, structured and orderly, and then it switches over to turbulent, where it becomes a chaotic flow going up and down and in twirls. So the critical Reynolds number in a brazed plate heat exchanger from laminar to turbulent is much, much lower than in a tubular heat exchanger, and that is because of the brazed plate has a smaller hydraulic diameter and a much more complex geometry that is inducing turbulence. So in a tubular heat exchanger with a smooth pipe, the switch from laminar to turbulent is about 2,300. And in a brazed plate, we have a critical about 150, and then it moves over to fully turbulent at about 500. Why is this important? Well, at laminar flow, you will have a velocity gradient, so the flow will be very slow in the corners or close to the wall of the heat exchanger. And this will allow the suspended solids to settle, and it will also drive up the wall temperature, which will be important for scaling. So laminar flow is bad for microfouling, and it's bad for scaling. And turbulent flow is good against microfouling because it keeps the suspended fluids running around, and it will also make the wall temperature lower because the heat transfer is much more efficient. So that's why turbulence is so important. What I also like to point out is the optimized flow area that I mentioned before, that since SWEP has been able to work with a whole plate, since it's a brazed plate and not a gasketed, we see that we have turbulence in all parts of the heat exchanger, and there is no dead areas or low flow zones. Let's move over to shear stress. Shear stress is the cousin of turbulence, the strong cousin, I would say. So shear stress is the force that the fluid apply on the heat exchanger wall, which is what we call the self-cleaning effect. So a high shear stress is able to clean away dirt that is starting to settle. And there are several independent fouling studies that I'm not going to show here because I don't have the time, but show that there is an asymptotic fouling level, meaning that fouling starts and then evens out to steady state depending on the shear stress. So we know that with a high shear stress, we have a self-cleaning heat exchanger. Shear stress is well known as an important factor, and if I go to API 662, American Petroleum Institute, and is also copied in the, or is also available in the ISO 15547. This is for recommendations for working in the oil and gas applications. So for plate heat exchangers in oil and gas, a 50 pascals shear stress is recommended. SWEP has found that this is good. More shear stress is always good, but we suggest that even 25 pascals is also a good value working in HVAC and industrial applications. Even if the water is not perfect, it could be that HVAC and could be that oil and gas is more demanding than most of the applications that we see. We also have applications with less than 25 pascals and also lower than 10 pascals of shear stress. But what we recommend then is that when you're below 10 or below, we would recommend that for closed loop applications with controlled water quality. Because if you have a fairly good water, there will be no fouling in some way. If you have a reasonable good water and it's a closed loop and there is no infiltration of clay and dirt and stuff like that, you don't need to work against the fouling because there is nothing to foul. But otherwise, if to be better safe than sorry, 25 pascals is our our gentle suggestion, and this is also we had this disclaimer in the beginning. There's another thing here. Many of you like very high thermal efficiency. So what do we mean by that? Well, one way of measuring thermal efficiency or efficiency is LMTD, logarithmic mean temperature difference. And the lower the LMTD, the more energy you're extracting for the system, more energy efficiency, which is good, right? And brace plate and plate and frame, they're really good in delivering energy efficiency. But when the LMTD is request LMTD is reduced, right? Squeeze more and more energy out of the system. The surface area needed will increase exponentially. It's not linear. It goes up very fast, right? So what will that mean? So adding more heat transfer area means adding more plates. And keep your eyes on this corner here. So when we add plates, what happens then? Well, we will have more channels, right? But we will have the same flow, but everything else is the same. But if we have more plates, more channels, and the same flow, we will have lower flow velocity, right? Lower flow velocity will have less turbulence, and less turbulence is less shear stress, and that's increased fouling risk. So, unfortunately, there is this trade-off that if a heat exchanger is supersized or oversized, I want the best now. If that is combined with a lower than optimal turbulence and lower than optimal shear stress, you will have a very good performance day one, but due to the increased fouling, if the system is prone for fouling, of course. If it's a clean system, whatever I say now is not applicable. But if it's a real life system with fouling, the oversized system will foul faster and will go down to a lower performance in a shorter time than a heat exchanger that was less plates, had higher turbulence and higher shear stress, and will survive better. So this is why, as a general, we would like to help you to find the best balance between performance and fouling risk. But depending on what is your need and what is the application. But as a general, SWEP does not recommend use you oversurfacing when we're dimensioning our heat exchanger due to the risk of reduced shear stress. You are of course free to do this anyway, but that is why this webinar is for you to know when not to do it too much. So the last of the big three, scaling, the barrier reef of fouling. Unfortunately, not a nice one. So what is scaling? Scaling is salts. So it's not a suspended thing anymore. It's actually, you know, dissolved in the water. So it comes in. You cannot stop it by any filter or anything or mechanical filter, and then it will precipitate and form scale if the salt is the type that where the solvability decreases with temperature. Those are typically carbonides and sulfates. And the main important things here is the water composition, the pH, and the wall temperature. And the only thing that we can really do something about is the wall temperature. So that's what we'll focus about. I go back. What do I mean with a barrier reef? Well, scaling is it's I would say the common denominator for microfouling. It's where we see microfouling, there's typically scaling as well. They act as a couple. And the problem with scaling is that it starts to it sort of say it builds up inside and captures silt, etc., that maybe normally would just pass by. So if you have a water that is prone for scaling, keep an eye on it. Keep an eye on the pressure drop over the heat exchanger, etc., because there is a higher risk that you will come into a fouling issue. Where do we see scaling the most? Well, hard water is the most driver, as I mentioned before, water composition, and so if you have an open loop water source where there is new fresh water all the time, that is hard. It could be hard tap water, could be again cooling tower, surface or groundwater. Then that's a high risk of foul for scaling. In a closed loop system, again, if there is no infiltration, the risk of, even if the starting water is kind of hard, if it's a closed loop, the risk for scaling is not so big, since it will be a finite amount of salt to precipitate, and then it will not be so much anymore. But then, of course, if the makeup water is very hard, and it will be more and more makeup water over time, this will also build up scaling. But it's mostly an open loop issue, scaling. How to avoid scaling? SWEP is, for example, using the Langelier index, which is a commonly available water quality measurement. And when it starts more than positive 0.5 upwards, the risk of scaling increase. So if it's far above 0.5, you are in a scaling country. The reduced water temperature, as you see, the solubility of sulfate here, with a higher temperature on the x-axis, we see that they go down, meaning they will start to attach to the warm surface. What we have seen is that when up to 60 degrees or 140 degrees wall temperature, the scaling issue is not that bad. Above there, it starts to degenerate kind of fast. To avoid a wall temperature, you can work with a lower water temperature, and you can also choose a high thermal efficiency of the heat exchanger, and that is, of course, the brace plate. Keep water flowing. What I mean by that is, if you have a hot water application, and then you just turn it off and turn it on and turn it off, turn it on. If that happens often, when you turn off the cooling water, or the cold side, so to say, you will allow the heat exchanger to go up in temperature, maybe above what is the normal operating temperature. So we have seen that scaling is more prevalent in applications where there is a lot of starts and stops. So if you're able to have a soft stop and running the cold water side for longer than the warm water side, you will reduce scaling for sure. Turbulence and shear stress will also be a partner here. They will be able to clean away some of the scaling building up, as with the microfouling. And there is a teaser here. For tough scaling applications, SWEP recommends Silix, a silica oxide protection for brazed bed heat exchangers. So SWEP has a technology where we add a specially developed silica oxide protection to the heat exchanger that will reduce the risk of scaling, will make it more easy to. It will make it harder for scaling to attach and easier to take away, and it will also protect against corrosion. I will not speak more about Silix on this webinar. There is a link in the material when you get it. There's a link to our European webinar that was earlier this summer, and we're going to have a North American Silix webinar a little bit later this fall. So please stay tuned for that one. Wow, a lot of words here, right? So where are we now? So we are to compare fouling in the brazed plate with the plate and frame and the tubular heat exchangers. So if we now look on the 4 types of heat exchangers, shell and tube, coaxial, plate and frame, and base plate, and look on the macro fouling, who is the winner here? Well, it's actually shell and tube and coaxial. Why are they the winners? Due to the plate and frame and the brazed plate heat exchanger, we have the small hydraulic diameter, or so to say the small distance between the different plates. A shell and tube or coaxial will be able to swallow a bigger stone, right? The pass-through diameter is absolutely the better here. That is why we continue to recommend strainer. Put a strainer, and so you don't get your port area clogged up. When it comes to microfouling, the suspended solids, I would say that the shell and tube is the worst one there, because it's designed with the baffles and everything. There is a clear areas of dead zones where you will have buildup of fouling immediately. A lot of tests showing that. A coaxial is also not a really good example there, because of the laminar flow that you will typically have, and close to the wall you will have a laminar flow giving precipitation of silt. The plate and frame and the BPHE, I give the plate and frame and BPHE more or less the same. I give ourselves 1+ more, which I will explain here. So when it comes to the shear stress, the plate and frame and brazed plate are about the same. Sorry. But when it comes to turbulence and the full flow and the no dead areas, the brazed plate, again, thanks to this CFD or the genetics, the BPHE genetics that I speak about in the beginning, a plate and frame type of plate, well, since they have gaskets covering one of the connections, one of the port sides here, they will have a low flow area in this area and this area that we're able to to design away from. So that's why I see the brazed plate as a winner in this one. When it comes to scaling, then again, the shell and tube and coaxials, they are I rank them below the plate and frame and brazed plate, mainly because for the same surface area, the plate and frame and brazed plate heat exchanger are thermally outperforming the shell and tube and the coaxials. Why is this important? Well, as we discussed before, the wall temperature is very important, and for the same water temperature, I said I used 140 Fahrenheit as the maximum temperature that we would recommend as a leaving water temperature. But to have 140 Fahrenheit water temperature, the coaxial and shell and tube needs to have a wall temperature well above 140 Fahrenheit, where a plate and frame and brace plate can work with a much tighter LMTD due to the increased turbulence and the geometry of the plate type heat exchanger. So this is the assessment. Again, I'm not saying that I am completely non-biased here, but I try to discuss the pros and cons as fair as I can. So moving on. Let's see if I can go moving on. Yeah, now we're in the fun facts. There's been so much talk about problems and fouling and scaling, etc. So I just thought let's put in some real information here. Over the last decade, SWEP has supplied about 25 million brace plates for tap water heating. Tap water heating. Why do I mention that? Well, that's where we have tap water of different type of hardness all over the world, and so the scaling is an issue. So, but with this, since we've been supplying to combi boilers, hot water heat pumps, energy recovery in chillers and refrigerator systems, solar heating, etc., that all were going towards sanitary water or shower water, right? This is a combi boiler, and this is a heat pump or an energy recovery module. I would like to argue that our experience show that we know that scaling is a potential problem and fouling too, but we should respect them. We should design around them to avoid them. We should be diligent of looking in the water quality. We should respect scaling and fouling, but we should not fear them, because I do not see scaling and fouling as such a big threat, because otherwise I doubt that we would be able to be so successful of supplying to this kind of applications. That's so let's move on. If fouling hits the fan, so now we have discussed what kind of foulings there are out there, how to avoid them with our best knowledge. But if it happens, if fouling happens, what do we do? First, you have to know, how do I know my heat exchanger is fouled up? And what you should know now, is that all fouling types increase the pressure drop over the unit. This normally results in a reduced flow, as the pump can't handle the extra resistance. So a higher pressure drop or lower flow in the system could be an indication of this. Microfouling, there's the suspended solids, and scaling also insulate the heat transfer surface, as we see here, clean and dirty. So if that will further increase the pressure drop, but it will also reduce the heat transfer. So what to look for? If the pressure drop starts to go up, and an indication that most plate type suppliers recommend is 30% higher than the nominal. But also if you start to measure an increased LMTD or a reduced efficiency, or if you have a chiller or a heat pump, if you see a rise in a discharge pressure or a reduction of the suction pressure in the evaporator, that is a possible reason for fouling. We have some tools in SSP, our calculation software. It can help you by using the model that you're using, the number of channels, and please note channels, so it's not plates. So if I'm writing 100 channels, that means 200 plates, since it takes 2 plates for a channel. And then you can enter the flow, and in this pressure drop tool, you will be able to get what is the pressure drop that you're supposed to have over the heat exchanger with this data. And then you can enter your own measurements, and you can say plot them out and see if I'm getting inside the danger zone with more than 30% of the pressure drop compared to the nominal. And if so, yeah, you should probably talk to a cleaning in place expert to see what you can do about it. Before doing that though, make sure that the filters are clean, the strainers are clean, the pumps are functional, and all valves are open in the right position to rule out that all what you have done is not due to the fouled up heat exchanger, but because something else is wrong in the system. That will save you time and money sometimes. SSP, I will not go through SSP a lot today. This is actually it, but it's also in SSP where you find the Reynolds number and the shear stress value, as we discussed before. So now you know that you have fouling. What do we do then? Well, of course, this is when we do our mechanical cleaning. We dismantle the system. We disassemble the whole heat exchanger. Make sure that you have the service area available. We clean it with mechanical and high pressure cleaning. We assemble and seal it again. Test it that it's working. If it's leaking, we might have to open it again and maybe change a plate or a gasket that were damaged. And if we open it, maybe we should change all the gaskets anyway, which would add some extra time. And there are SWEP do not do this, but what the literature we found is that a complete breakdown like this is 2-3 working days. And I would say that it's always better if you can avoid mechanical cleaning. It's more time effective and it's more cost effective to do preventative care and cleaning in place. I also know of situations where a plate and frame heat exchanger that needed to be opened and reconditioned, it was more economically viable to buy a new heat exchanger because it was too expensive to work on it. And since the brazed bed heat exchanger does not have gaskets at all, you will not find yourself in this situation. So what's the other option? Well, that's cleaning in place. SWEP we have all our own material on recommendation on cleaning in place, which some of this material is included in this presentation today. We have seen that cleaning in place works, but SWEP is not a cleaning in place expert. We are not a cleaning in place company. We work with companies that are expert in cleaning in place and preventative maintenance. And the ones you see here are a group of companies that we know are active in North America. And if you are coming from outside North America, please contact your local SWEP office to find out who we work with in your area. One I would like to introduce to you a little bit closer is Goodway. Since Goodway and SWEP have had some case stories put together for cleaning in place, and SWEP and Goodway has also collaborated to make sure that the scale brake multipurpose MP cleaning fluid is 100% compatible with the SWEP heat exchanger, so it can stay in there for long periods of time without any risk of corrosion or any other types of damage on the heat exchanger. So this cut sheet here with information of the Goodway's scale brake is also one of the downloadable handouts. One of the case stories that we did together was with a mutual customer, Multistack Chillers. And this case here was a sporting facility somewhere in the south. Would had a Multistack MS85 chiller, or quite a lot of them. What they noticed was that the compressors were tripping on the high pressure switch. And that's normally not the case. That shouldn't happen, right? So they did a measurement and they seen that the discharge pressure was up 165 psi from when it was originally commissioned. And I don't know how much you know about refrigeration system. That's a lot, right? Especially if the compressors start to trip as well. According to Goodway, or Tim Forgo of Goodway, a cleaning cycle will normally be 4 hours. In this case, if I'm allowed to say that, they left it overnight because they wanted they thought, well, let's leave it overnight. Why stop now and put up? So they left it overnight, which is not a problem since we have this tested for compatibility. When they came back and flushed it out, they have reduced the discharge pressure with 40%. They were back at factory specification, and when the system was operating at full capacity, they had, by doing this cleaning in place, they saved $348 a day. Another one, another of these cleaning in place is for a completely different application. It's a waste energy power generation system. Again, operating with high water temperatures. Again, scaling is an issue, and by cleaning it out, we went from a dark reddish brown. This is not the copper you see here. This is bad stuff, right? Scaling is even if scale is a white salt, since it absorbs the solids, it always looks a little bit brownish. After cleaning, you could see yourself in the reflection again. This is not us. This is not SWEP at all. This is done in a different continent even, but I would really like this YouTube film, and I would recommend it. It shows a plate and frame in an oil and gas application, and it's completely clogged up in the entry, and it's a plate and frame of a about a man height, so it's maybe 5 feet tall, so it's absolutely possible to open it. What I found interesting in this down-to-earth gritty application was that they chose, with a heat exchanger that was this dirty, they chose to do cleaning in place, and they reached this kind of cleanness by doing it. I like this one because it shows that it's not only SWEP who is making brazed bed heat exchanger that you cannot open that is promoting cleaning in place. Cleaning in place is the more time effective and cost effective and effective cleaning method when fouling hits the fan. I do not own any rights here. I just give this as a something to follow up on, and also looks kind of funny when you see them. So now we are back where us who stayed through the whole IKEA warehouse. Now we're back to the to where you buy the hot dogs. I have gone through this before, so I will not do it so much, but now you know what I mean with Reynolds 150. This is the starting point. If you can reach 500, please do. Shear stress 25. If you're in shear stress 10 pascals, don't panic. If you're in 2 pascals, don't panic. If you have a clean and controlled closed loop system, this one here is for that when you don't know, right? When you're building a system but you don't know really where it's supposed to go, have 25 as a good reference point. Know your pressure drop, because maybe that's not your problem, but you should have it maybe in your manuals. Your customers, when they install it, they should measure the flow or the pressure drop so that they know what it is, and then they can compare it after 1 year, 2 years, 3 years to see, has it decreased a lot? Do I need to clean this out? The weak spot for the brace plate and the plate and frame is the blockage, the macro fouling, as I call it. The best way is to have a strainer. Stop it before it goes in. If you get it in the ports, then that's a good starting point for the rest of the fouling, and it's so easy. Make sure that you have the flow that you think you have. If you plan it for 10 GPM but you have no clue if you have 1, 10, or 100, you are asking for problems, because it's normally, if you don't know, it's normally 1, not 100. And then when it comes to system water treatment, again, water quality, water chemistry is an enormously big discussion that we are not expert. There's a lot of companies that are expert in water treatment. So if your water is kind of crazy, involve a water expert to find out. I mean, then Goodway and the other guys, they will be able to help you a lot here. That's actually it. I have more slides here, but I think that I've been talking for 57 minutes. So for those of you who wants to log off now, thank you very much. We will send out this presentation soon, and it will come also on YouTube, so you can see it again. And if there are any questions, these are the questions we got on the webinar for fouling and how to avoid it. So let's get to it. Does all application need 25 Pascal shear stress to avoid any fouling buildup? No. For applications with a known and safe water property, like closed loop or even tap water, microfouling is very, very uncommon, and it's safe to work with a lower shear stress than 25 pascals. If there are no dirt in the water, there is no reason to have a self-cleaning effect to keep away the fouling. However, if the turbulence is getting low, and especially below 150, the reduced turbulence will make the heat efficiency suffer. So keep away from that. As always, it's always recommended to have a 16 to 25 mesh strainer to avoid any macro fouling, as that is not dependent on the shear stress. But keep away big stuff from getting stuck in the port, and you will not have any problem with this application. One person asked, what channel velocity should I aim for to have the sufficient shear stress? And to that, I have to answer, it depends. As we can see here on the right, the brazed plate technology have several different plate types, high thermal plates and low thermal plates. We have different pressing depth. We have asymmetric and symmetric plates, which I go through in another webinar you can find on our site. But due to the different geometries, you cannot immediately link the flow velocity over the plate to the shear stress. And to illustrate this, I took two heat exchangers of the same type, the 427 type, with a high theta plate and a low theta plate. If they are using the same flow, they will have the same flow velocity over the channel, but the high theta plate will have 85 Pascal shear stress, and the low theta plate will only have 22 Pascal shear stress. So flow velocity is not a good indicator for shear stress, but you will find the information you need in SSP. Another question related to the shear stress that we pointed out in this presentation was if there is any relation between the pressure drop on the water side with the shear stress. And the answer to this is yes, there's a pretty good relation between those two. The graph here on the side is a simplification, so I would like you to use the SWEP SSP software to find the real values. But as an indication, if we're looking at a shear stress of 10 pascals, that will be in the range of 1 psi pressure drop. 25 will be in the range of 2 to 2.5 psi, and 50 pascals will be in the range of about 4.5 psi. So regardless of the type of if it's high theta plate or low theta plate, this is indicatively true. But for details, please go to SWEP SSP. One question was, what oversurfacing does SWEP recommend when designing a brazed plate heat exchanger? Adding an oversurfacing or a safety factor when designing a heat exchanger means adding more plates. Adding more plates means adding more channels, and that will reduce the velocity over each channel. Reducing the velocity of the channel reduces both turbulence and shear stress. Due to this, SWEP does not recommend to use any oversurfacing when designing a heat exchanger. We propose to right size it from the beginning instead of oversizing it. However, if you add plates and you still remain within the recommended levels, for turbulence is absolutely above 150. For shear stress depends on the dirtiness of your system, as we discussed before. As long as you stay within those recommended levels, there is no immediate downside for adding a few plates more, a little bit more surface area, more than you will have a higher cost of the heat exchanger. So it's in some way up to you and your preferences. However, if we are talking about an evaporator in a refrigeration system, oversurfacing can have other negative implications when it comes to distribution of the refrigerant inside the plate pack, and their oversurfacing can be more critical. So we remain of not recommending oversurfacing, but more about evaporators in a later webinar. One question that I actually couldn't answer was what kind of CIP fluid is recommended by SWEP, and what kind of concentration of acid do we recommend? Well, first of all, we recommend organic acids and not mineral acid. And a mineral acid could be like hydrochloric acid or HCl. It's a very good descaler, but it can cause corrosion inside the heat exchanger if it's circulated for a prolonged time, or if this hydrochloric acid is not washed out correctly after the cleaning in place procedure is done. So SWEP recommend a CIP fluid based on, for example, citric, phosphoric, or oxalic acid. We generically, from a generic point of view, recommend 5%. But then again, SWEP is not a cleaning in place expert. So what we do is we talk to our cleaning in place partner, and then we ask them to do tests with our heat exchanger to verify that there is no corrosivity. And that is, for example, what we did with Goodway to make sure that their cleaning fluids can stay in overnight to clean out a very dirty system so that it's back to factory specifications in the morning. The last question for today was, what is the maximum total hardness of water to work in the brazed plate heat exchanger? And the SWEP brazed plate heat exchanger can work with a very wide variety of water chemistry and hardnesses. Of course, the harder the water, the higher the risk of scaling as the wall temperature increases. Our recommendation is to calculate the Langmuir Saturation Index, LSI, which you can find free calculators online, to enter the hardness, the different ions that you know that you have in the water. You have to enter the highest system temperature, the highest temperature that you will have of the water, and then you will be able to calculate if you have no, medium, or high scaling problems. It's typically a value of, if you're in the scaling zone, it starts at 0, 0.5, 1, 2, 3, 4, with a higher scaling risk as the number become higher. If you have a water quality that is of high scaling risk, we would recommend plan for CIP, plan for cleaning the heat exchanger in preventative maintenance breaks every 3 months, every 6 months, every 12 months, whatever you need to keep your heat exchanger clean. If it starts to scale, it's not a problem if you plan for it. Another possibility is to soften the water to make it less prone for scaling. It's of course also a possibility. What I would like to say that always when you tinker with water chemistry, there is a risk that the water become corrosive. So we also have a water composition sheet, or ion composition sheet rather, that gives you an indication of what ions to look out for, what is the maximum levels for the plate material 316 and copper. Those are the two most common materials in our brazed plates, but we have other one, as you see. so that you keep out of harm's way. So good luck and thank you very much.